On some level, I think that I enjoy not knowing things and making that fact very public and obvious. It's kind of a form of masochism.
You're listening to Marianne Writes a Programming Language. And I'm Marianne.
This episode is going to be a bit of a detective story. When I first started planning out this block of episodes, should I call it a season of episodes? Well, I guess it is. Okay, this season of episodes. I looked at the topics I wanted to explore and thought, oh, well, actually, some of this stuff is more interesting if I talk about it in terms of types. So let's plan for an episode about type theory and type checking. That will be fun, right? And as always, I naively assumed that I could just type how to implement a type system into Google and piece together an understanding from a bunch of tutorials, except no such tutorials exist. Or rather, tutorials do exist, but there was a huge gap. I found some great tutorials about typing in general, static versus dynamic, why certain languages are stricter than others. These are tutorials designed to teach programmers how to interact with the type systems already implemented by the languages they use. Then I could find a great set of tutorials about type theory, all the different types of algorithms for inference and the math behind them. But I couldn't find anything on what implementation of this theory within a compiler looked like. And now I know what you're thinking. Marianne, if you know how to program and you understand the theory, why would you need someone to tell you how to implement something? And the answer is that type theory is a formal system of logic. So the computer science papers explaining the algorithms explain it in terms of logic programming and theorem proofs using languages like OCaml and Haskell, both of which have abstractions that do not exist in most general programming languages. If you remember the episode on BNF grammar, you'll recall I got myself into a similar situation then, only this time, I didn't find a secret resource that clearly explained the correct approach and made everything click together. This time I had to scrape together bits and pieces of information, looking for the next Google-friendly keyword I could use to track down more information. It was a slog. For close to a month, I was reading and searching and reading and feeling like I was getting no closer to understanding how to implement a type system for fault. It felt impossible. So this episode is that story. Stage 1. I don't understand what the phrase type system means. At various points during my research, I would ask people in communities I frequented if they had any recommended resources to better understand type systems. Most of them replied, "What kind of type systems?" And truth be told, I still don't know what the correct response to this question is. Are you asking if I want to do static versus dynamic types? Are you asking what inference algorithm I want? Whether I want polymorphic types or dependent types or linear types? There seems to be so many options on the type menu that I don't have a clear sense of what the top level filter should be. But through searching and not finding what I was looking for, I realized that type system is not the correct phrase for what I meant. At least, not exactly. When I would search for information on type systems, I would get lost in descriptions of type inference. Type inference is a small part of a type system, but nowhere near the complete story. This is like searching for a cake recipe and finding nothing but various opinion pieces on sugar substitutes, then trying to get a clear picture in your mind of the process of baking a cake from reading a 20-page analysis of the correct ratio of coconut sugar versus almond sugar versus something else. The explanations I found around type systems tended to skip all the boring foundational components of type systems and go straight for the bits where you get the most debate and research. Great if you already have a CS degree, frustrating if you're coming in completely cold. Basically, a type inference is when your program does not declare what a variable's actual type is, but you're going to infer it or guess it by comparing its characteristics to the characteristics of known types, which the programming language has defined and which have certain rules. If the variable passes all those rules, it can be thought of as having that type. Type inference is important because declaring types all the time, every single time, can be pretty cumbersome. Remember that it's not just variables, it's also values returned by functions. Some languages, like Go, have very simple unidirectional type inference, meaning that if I store the output of a function in a variable, Go does not need me to declare that variable's type, because Go requires me to specify the type the function will return. If the function returns type int, then Go's compiler can infer that the variable storing the value returned from that function is also type int. Other programming languages are less strict about when and how you must declare types, or whether or not a variable can do something like store data of type int and be reassigned data of type string. If you've programmed in multiple languages before, you've likely seen many variations on syntax around typing. The more flexibility you give the programmer, the more complicated and necessary inference becomes. So when you ask people about type systems, they immediately jump to talking about type inference because it feels like the meat of the issue. I see myself doing this a lot with topics that I know a lot about too. I skip the parts I already understand because I don't remember what it was like to not understand them. I forget they might even need to be explained in the first place. One of the people I talked to in my quest to understand types is Ron Garcia. Ron is an associate professor of computer science at the University of British Columbia. He's got a patient and very accessible style, but still, when I asked him about type systems, when you explain type systems to people, like what actually is a type system?
Right. So basically, I gave a talk at Papers We Love a few years ago. It was about type systems, but it was mostly couched in a particular paper, one of the first kind of really serious formal attacks on type systems. It was done by Robin Milner, and like that paper, like really, I've read it way too many times, went over my head even more times than I've read it probably, but at some point, like there's bits in it that that click.
The paper he's referring to here is Robin Milner's A Theory of Type Polymorphism in Programming. Right, so straight into the deep end here. But seriously, it's a great talk, and you can find a link to it in the show notes at dev.to/Belmar. But as we talked about it more, Ron actually has a great metaphor for thinking about type systems that would ultimately help me break down and organize my research.
It's a number of sentences that you can write about a program. So I can say, if I have this chunk of code, like let's say I have x plus y, like, oh, here's a chunk of code. And you're like, yes, that's code. It's not a program, but it's a little piece of code. Then I want to ask a question about it, or I want to make a statement about it. Yeah. And a statement I might make will be, supposing x has type int and y has type float, then this little piece of code has type float. And that's just like, why? Well, because the programming language designer said so. You're like, shut up. But what's really sort of happening is then you've basically written a bunch of stuff and you've made like a statement, and this is sort of the language of the type system. It's like under a set of assumptions, this piece of code, under a set of assumptions that are about the code and types, this piece of code has a type.
Yeah.
And then it's like, okay, so all that told me was syntax, which is basically we often in at least in formal programming languages, or if you're writing down a specification of how types work in prose, you write things like that. You're like, yeah, like the type of this thing is this. And then there's like, well, okay, so now I know how to, that's just parsing basically. So you can think of type checking as an extension of parsing. It's like parsing, but even worse. Like not only does it have to parse, but it has to pass all of these rules that say like, we're going to say this thing has type int, and it's like, oh, and by the way, since your function takes an argument and the first argument has to have type int and the second argument has to have type float, like you're only allowed to put expressions that I can say like, this one has type int and this one has type float. So it's okay to make this call.
Yeah.
So that's sort of the syntactic part of typing. So I say like, just like programs have syntax, type systems have a syntax. And the syntax is basically, what can I say about a small chunk of code given a little bit of information about the surrounding context, which is often things about the variables that are in that expression.
Typed systems are programming languages within programming languages. That's not going to make sense right now, but keep it in the back of your mind. Over time, what I realized I was looking for when I asked about type systems was type checking. I wanted to know how to implement a type checker first, then bring all the mechanics of type inference and composite types and polymorphism and all that other stuff. I needed to be specific in my search. How does a type checker work? Of course, this was not an easy thing to Google. Most of the blog posts I found start with the formal logic behind types, vomiting out rows and rows of Greek symbols without a key or explanation, before getting into a code sample in a general programming language, if they got there at all. I ended up just reading source code, first pulling up a couple variations of Thorsten Ball's monkey that had type checking added to them, then by digging into the internals of Go's compiler. Each time I found myself looking at a recursive function, walking the AST, and subjecting each node to a set of conditionals. Is that all there is? You mean all these complicated looking formulas with their fancy unexplained Greek letters boil down to a bunch of if-else statements? Really? Stage 2. I realized that types are like formal specification. On the surface of things, types can seem like a very pedantic topic because many of us got our starts programming languages that use dynamic types and aren't super strict about them. When that's your reference point, caring about types can feel like caring about the Oxford comma. What's the big deal if people don't get it, or they don't use it, or they use it wrong? But what I discovered while wading through all that information about type inference algorithms is that type systems actually create boundaries keeping the program from drifting into undefined behavior, just like a formal specification should. Let's say, for example, you want to evaluate the expression x equals 10 divided by 4. Is the value of x 2, or is it 2.5? You can probably think of a programming language where the answer is different. So maybe we're working in one where 10 divided by 4 is 2.5. Is 10 plus 4 then 14.0? Why not? Floats and ints are handled differently inside the computer, so programs need to have clearly defined rules identifying what operations can be run on a piece of data and how to interpret what value comes out as a result. These rules are types. Without them, it would be possible to push the program into unexpected and potentially dangerous behavior. Type systems have several different kinds of rules. There are rules defining the characteristics of each type, rules about what operations can be performed on each type, rules about what types come into functions and what types of values come out of those functions, rules about how types relate to one another and whether conversion of one type to another is possible, and if so, how. All these rules should make a kind of proof tree, and that's what powers type inference. A proof tree is a type of Boolean logic, a set of true-false questions delivered in a certain order to prove whether, in this case, a variable of an unknown type has all the characteristics of a specific type. Okay, cool. So the type checker walks the tree, and the if-else conditionals are checking whether a certain node follows these rules. But where are the rules themselves? I think the type checking part was the easiest part for me to understand because having already gone through the construction of a parser, and I'm like, okay, now I got my AST, and like being able to go, okay, this should be the same type, and if they're not, or they're not like okay, then we'll throw an error. That all makes sense. But then I got to the type inference part of things, and like everything that I read was sort of documented in a kind of stuff that reminded me a lot of Prolog, which was like, okay, cool, that makes sense to me, but now I have absolutely no idea how to implement that within like a compiler, right? Or within essentially like an evaluation loop, right? Like I don't want to like port Prolog into my programming language to write these rules down. Like, how does the implementation of type inference like really look like in the wild?
Okay, so that's I'm gonna answer a different question than that one.
Fair enough.
Which is, but for what I hope is a good reason. And what I'm hoping to do is leverage off of the idea of parsing.
Yeah.
So when you learn, because in many ways, I think of writing a type checker as writing a parser on steroids, just because like type checking is like parsing, but worse. So when you write a parser, typically you have like a grammar for your language. And then nowadays you have a bunch of tools where it's like burka, magic, abstract syntax tree pops out.
Yeah.
But there's sort of another way of looking at this process in multiple steps. So one of them is that whenever you write a grammar for a language, and I'm just skipping the lexing part. Let's just make believe lexing was solved. So you have a grammar and it's got like a bunch of stuff. You can think of that as a definition of it's a really weird, not weird, it's beautiful, but it's just a definition of a data structure.
Yeah.
And that's the parse tree. So the way I usually describe it is your parse tree is like every production on the left of like the arrow is it's like a type, and then every non-terminal is a type, and then every production is a different data structure in like a union type. Basically, you're like, oh, it could be any of these three things. And then it references itself sometimes, or it references somewhere else. So you have this sort of tree structured data type, which can be like an arbitrary arity tree with a little bit of information. And the cool thing about that is that if you think about it that way, when you have a parse tree, usually the way we think about parsing is, oh, give me a string of tokens and I will give you this parse tree. And the thing I like to think is you can think about this backwards. You can say, give me a parse tree and I will give you back the tokens that built it. Exactly.
Yeah.
Like with nothing different. And so then parsing is just the process of running a program backwards, which is like, oh, like here's a set of tokens. I make believe that there exists a parse tree that produced the tokens. Your job is to give me the tree.
Uh-huh.
And the amazing part is that you can often do this. Like, it's like, oh, like I run it backwards. Like, it's almost like, oh, somebody in their mind had an idea of the tree and then threw it out and all you have the tokens. And you're like, let's recover exactly the thing they were thinking about their notation. And then it's too much garbage because there's like all this weird stuff you have to do in a grammar.
Right.
That like, oh, all these parentheses. I don't care that you have like 7 like layers of parentheses around 5 plus 9. No one cares.
Well, we're not writing a list here, so we have a few.
Well, no, I mean, like some people will, meaningless parentheses. Yeah, in Lisp, right. you care about the parentheses, but in like Python, some peculiar programmer who likes to always like, I just really want to make sure that my precedence is right, so I'm just going to add extra parentheses. Like nobody knows. Like just tell me it's like 5 plus 9. We're good. So that's where you go from the parse tree to the abstract syntax tree.
Right.
Where it's just like, we're going to forget all the uninteresting details of how your program was written. And yeah, I can get you back a string of tokens, but it's not going to be exactly the same one, but it will mean the same thing. So I know this sounds like, what does this have to do with type systems? So,
it does, but I'm waiting.
Totally does. Cool. So the thing that you saw that looked like Prolog, where you have like a horizontal bar, some stuff on top and stuff on the bottom, that is a grammar.
Yeah.
It doesn't look like one, but it's a crazy grammar.
Yeah.
And it describes a data structure, which is what we would call a typing derivation tree.
Okay.
So the way you can think of a typing derivation tree is it's like a data structure that has lots of extra annotations in it. Like in a production compiler, what you would do is like, oh, I have an abstract syntax tree with a little bit of decorations. Like I've got like an extra field called what's my type, and then I stick things in it. This is worse. This is like, we are going to just like stuff everything everywhere. You're like, dude, you already told me that it was an int. Like, come on, you told me it was an int. Yes, I already know that the context is all of this stuff. So you can take all of those rules and you can write a data structure that captures it.
Stage 3. Type systems are programming languages in programming languages. The phrase data structure really threw me off because I could envision what that should look like, and then I couldn't find it in code. I was looking for a tree, and I couldn't find any trees defining types. Then I found a slide deck from Princeton University's COS 320, Compiling Techniques, that walked through the various components of a type system bit by bit, and it hit me. The if-else conditionals are the tree. Proof trees for type systems are often described as a grammar, but unlike the types of grammars used by parsers, they don't exist in a separate grammar file. Come to think of it, if you hand wrote your parser and lexer, your grammar probably wouldn't exist in a separate grammar file either. So maybe that's more about auto-generation of parsers and lexers than it is about grammar files being significant. Anyway, the conditionals are the tree. When I could finally see a type system with all the boring and unsexy bits left in, I could see why Ron described it as a programming language inside a programming language. You start with a set of rules that define valid statements, very much like a grammar. Then you write a function that parses an AST and compares it to that grammar. And that function either throws an error or it returns that AST with inferred types filled in or types converted as needed. It's very much like the foundations of the compiler itself. Ultimately, I want to keep Vault's type system pretty simple. No composite types, no reassigning variables to different types than they're declared as. I have to decide whether to change the grammar so that functions can specify what types they return, or I have to figure out how I want to do type inference. But the only way to answer those questions is to implement it and see what kind of problems I have. In the end, the thing I learned is that the world of types is full of interesting ideas once you get the hang of them. So a lot of the papers that I've looked at that you've been involved with are about these things called gradual types. Like, what are gradual types exactly?
Oh, yeah. Okay. It's like, oh, dear. So gradual types is, as a broadly speaking, gradual typing is the idea that type systems are really helpful. Like they're type check, they're spell checkers, they're grammar checkers. So they're wonderful that way. Type checkers are terrible, just like spell correction is on a phone. It makes my life miserable. So it's like simultaneously miserable and wonderful. And and especially in like a large code base, it's really nice to have something that gives you some guard and sometimes doesn't get in your way. So the research that I've done on this is the idea that it would be nice to have like some code that's got these type checks in it, and they mean something. They say, like, if you give me certain kinds of data, I will produce certain kinds of data. And it goes even further. It's, I am expecting you to give me certain kinds of data, and if you don't, you're like, bad things. Don't do that, because it'll be hard to understand my code. I'm understanding this chunk of code on the basis of what kinds of inputs I'm expecting and what kinds of outputs I'm going to produce. And you've got this other piece of code which is like, yeah, I made no commitments. So it's useful to be able to protect this piece of code so that whoever's programming it, when they're on the inside, they can say, it's not my job to worry about what nonsense other people are going to throw at me, as long as I've stated my conditions for use and the promises that I'm going to, that the things I promise if you meet my demand.
You've been listening to Marianne Writes a Programming Language. A transcript of this every episode is available on the dev community. Just go to dev.to/Belmar to find them. That's dev.to/BELLMAR.
My conversation with Ron was filled with lots of fascinating information, more than I had the space for in this episode. So please, if you are a patron, go and check out the full version of this interview for all sorts of interesting commentary on types and type systems.
So that's even just like, if I knew what a parser would be useful for and when I could use it, that alone will get a working programmer very far, because the first goal is to recognize when you have a parsing problem. Recognize that it actually is a parsing problem, and then realize that thinking about it that way will just save you hours.